Hello, my calculus friends. We are ready to start our last part of our calculus part of the course before we start our vectors part. We need to review some things about trig, so sinusoidal functions, radian measure, trig identities. So I thought good to review this before we get into the derivative stuff, because without, some solid understanding of previous stuff, this is going to be a bit challenging. So first of all, let's convert 29 degrees to radian measure. What you should remember from advanced functions is that pi radians is the same as 180 degrees. So if I start with that, and you might have a different way of solving this, just depends on how you were taught. Pi radians 180 degrees. I don't really want 180 degrees. I want 29 degrees. So I'm going to actually divide both sides by 180 degrees. And that makes it 1 degree. Oops. 180 degrees. That makes that 1 degree equaling pi over 180 radians. I don't want 1 degree. What I really want is 29 degrees. So I'm going to multiply both sides by 29. So on the right side of the equal sign, I really have 29 degrees now. Now, if I look at that, that gives me that 29 degrees on this side is equal to 29 times pi over 180 radians. So 29 degrees is equal to this many radians. So I hope you remember that. You might have a different way. You might start with 1 degree equals pi over 180 radians and then go from there. Determine the arc length subtended by an angle if the radius of your circle is 5 centimeters and your angle is pi over 4. So we defined a radian measure, theta, an angle in radian measure theta, is just the ratio of the arc length divided by the radius. So if I have my radius and I have my theta, my arc length then can be gotten, if that's even grammatically correct, you can obtain it, the arc length, by doing radians, the radius times the radian measure of theta. So over here, if my arc length then will equal 5 times pi over 4, so that's 5 pi over 4 is your arc length. And if you want, if it makes you feel better, that's kind of not so quantifiable in your mind, you can actually do 5 times pi divided by 4. My arc length then is approximately 3.9 centimeters. Okay, so what's really happening here? If you think of your circle, and your radius of the circle is 5 centimeters, pi over 4 is really like 45 degrees. It means the length right here would be 3.9 centimeters, based on the fact that you know the angle subtended, or the arc subtended by that angle is pi over 4. Okay, so the pi over 4 is this central angle right there. All right, next one, again, if we want the arc length is going to equal the radius times the angle. Now that angle has to be in radian measure, so we've got to change 50 degrees into radian measure. So I know that pi radians is 180 degrees. I'm going to divide by 180 on both sides, and I'm going to times by 50 on both sides. That's going to give me 5 over 18 pi radians. I just reduced the 50 and the 180 by a factor of 10. That's equal to 50 degrees. So what goes in the bracket here has to be 5 pi over 18. So that's going to give me 25 pi over 18. My arc length then, if I do that calculation, 25 times pi divided by 18 is about 4.4 centimeters. Okay, so hopefully that's making sense and you can remember those things. You also need to know your special triangles. So I've drawn 2 triangles here to help you out. I didn't put all the labels on here. They're right angle triangles. This one is supposed to be isosceles with a 45 degree angle, or pi over 4 here, pi over 4 here, pi over 2 is your 90 degrees. That gives us the 1, 1, square root 2 ratios, or sometimes you see root 2, 2 as your ratios. The other special triangle is the 30, 60, 90. The 30 is pi over 6. So the small angle up here would be like the 30 or pi over 6. Down here, that's the 60, which is pi divided by 3. And then, of course, this is your pi over 2. Your smallest side is a 1. Your hypotenuse is the 2. And your middle side is the square root of 3, which is like 1.7, I think it is. Yeah, 1.73. All right, so those are things you should know. If you want the tan of pi over 6, I can look at my special triangle. Tan is opposite over adjacent, so that's going to equal 1 over root 3. Or if you want to rationalize that, times root 3 times root 3 over 3. I know some of your calculators automatically just spit that out and you don't have to use your brain, but I'd like you to be able to use your brain. The cos of 2 pi over 3. Remember pi radians is 180 degrees. I'm just going to draw a sketch here. 180 degrees. I'm going to put that angle in standard position. 180 degrees, so I've got 2/3 of pi. 2/3 of 180 degrees, which is 120 degrees. So 2/3 of the pi is 2/3 of the way to a half revolution here. So that makes this pi over 3 as my related acute angle. Pi over 3 then, and my side lengths then, if I look at my pi over 3 triangle, that means this is 1, but it's to the left, so it's -1. My hypotenuse is 2, and this went up, square root 3. So the cosine of that is adjacent over hypotenuse, or -1/2. So you should be able to reason those things out without having to use a calculator. All right, so those special angles that you should recall. The next thing we're going to do here is use identities to prove this is true, this whole shebang here. So we have some compound angle formulas happening here, which means you need to remember those things. Hopefully you have a summary sheet that you made when you took advanced functions, and you can pull that out and take a look at these things. But we're going to run through some of the things that you should know here. So on the left side of my equal sign, I've got the cosine of x plus y times the cosine of x minus y. Now, our compound angle formula says that when we have the cosine of x plus y, that is the same thing as the cos of x times the cos of y minus the sine of x times the sine of y. So I'm going to write that in, and the cos of x take away y is the cos of x cos of y plus the sine of x sine of y. And voila, with the magic of technology, that answer magically appeared. I've expanded it and then simplified it. So I had like terms here. I had a plus cos x cos y sine x sine y, but then I had a minus cos x cos y sine x sine y. So they canceled out. Now, what I'm going to do here is write everything in terms of cos, because you'll notice on the right side, I only have coses, I don't have sines. So I know by a Pythagorean identity, we know that sine squared x plus cos squared x is equal to 1. That's equal to 1. So that means that my sine squared x is really 1 minus cos squared x. And I can do the same with the y. So I'm going to replace the sine squared x and the sine squared y. So here I have done my replacement, and then I expanded and simplified the binomials here to get this. And then I'm going to put the -1 through that bracket and collect like terms. And again, here I have my simplified answer, which is equal to the right side. So a couple identities that are important there that you need to remember. There are some identities listed in your textbook on the front cover, just inside the front covers, or just inside the back covers. It depends on which version of the textbook that you have, but there should be some trig identities all listed there to help you out with that. All right, I have one more example here to go through. This example just involves sketching our graph of y equals sine x, but with some transformations on it. Remember that the number in front of the sine x, that's your vertical stretch, and that also works in with the amplitude of your function. So it has an amplitude of 3, a vertical stretch of 3. The 2 here is going to be your horizontal compression by a factor of 2. It's going to affect the period for your function. Remember, the period is going to be given by 2 pi, which is your normal period for sine x, and then we're dividing it by the k value here, dividing it by the 2. So the period in this case is going to be 180. One whole cycle is pi radians long. The +1 on the end is your vertical translation up 1. That changes your axis of the curve. So putting all of this information together, I'm only asking you to graph from 0 to 2 pi. I'm going to kind of map this out. So here's my 2 pi. That makes this pi. So halfway in between would be pi over 2. Halfway between here would be 3 pi over 2. This would be pi over 4. This would be 3 pi over 4. This one's 5 pi over 4. And 7 pi over 4. So that's how I put my scale on, is just that way it's easier for me to map that out. All right, I know one full cycle has to be completed in pi radians. So sine normally would be on the x-axis at 0, pi over 2, and pi, given that period of pi radians. It has an amplitude of 3. So when I go to my max, the max happens halfway between the zeros, the first set of zeros, and the min's going to happen between the second set of zeros. However, I also want to move everything up 1. So my axis of the curve is now going to move up 1. So the zeros are moving up 1. So I'm just doing my first cycle here, and then I'll repeat that. The amplitude is going to be halfway between here, between the 0 and the pi over 2. The amplitude, the maximum, and the amplitude is 3. So if this is 1 and I'm going up 3 from there, I'm going to be up as high as 4. So my maximum is going to be here at 4. My minimum is going to be down at -2 because it has to go down 3 units from +1. So my minimum has to happen between the second set of zeros. So here is one cycle of that function. And make sure you make it look curved. Don't make it look like it's jiggity jaggedy solid, straight lines. Like, don't go that's not how that works. And then I'm going to plot my next points here. My axis of the curve will have where my zeros normally would have been, my high point, and my low point. So I've got my 5 anchor points plotted here with a nice smooth curve. So hopefully you remember how to plot and what all the pieces of the transformations mean for you.